Hey everybody, welcome to Algebra, Section 2.8, Proportions and Similar Figures. So in our last lesson we talked about proportions, and what we're going to do is we're going to use the idea of proportions and use it to solve some mysteries concerning geometric figures and similar shapes. So by the end of this lesson you should be able to define similar figures and scale. You should be able to use proportions to find missing lengths in geometric figures. You should be able to use shadow similarity to find the heights of objects. And you should be able to use scale drawings to find missing measurements. So let's start off with a little bit of vocabulary. Similar figures. Okay, that's part of the title of this lesson. Similar figures are two figures that have the exact same shape but different sizes. So a couple examples of that. Here we have two geometric shapes. They're kind of weird looking shapes, but they're the exact same shape, but clearly different sizes. So that's what similar figures are. So let's take a look at some other examples from real life. Here we have Dr. Evil and Mini-Me. If you've ever seen the Austin Powers movie, Dr. Evil gets frozen and gets frozen in time, and his henchmen create a likeness of him that is exactly 1/8 his size. So, Dr. Evil and Mini-Me are similar figures. They're the exact same thing, but different sizes. If you haven't seen those movies, I'd go back and watch them. Austin Powers. They're hilarious. Here's another example of similar figures. The exact same thing, just two different sizes. Let's talk about scale. All scale is just the ratio between an object and its similar object. So for instance, here we have a guy building a scale model of a building. So obviously that building isn't life size, all right? But there is a ratio between the actual building and that model, and that ratio is called the scale factor. Here's an example of using scale with automobiles. So if we take a look at this, this car is not the real car. This car is a model. Okay, I don't know if any of you guys build those little model cars. They're about, I don't know, as wide as your head. Okay, they look just like the real thing, except they're very much smaller. So here we take a look at this top one. The ratio, the scale, is 1:18. That means for every 1 inch in the model is 18 inches in real life. Or for every 1 foot in real life, there's 18 feet, or every 1 foot in the model, there's 18 feet in real life. So if they tell you that the model is approximately 10 inches, then you can say, well, if it's 1 inch means 18 inches in real life, then 10 times 18, that means the car in real life is 180 inches, which 180 divided by 12, I think we're looking at 15 feet. That car is going to be 15 feet long. Okay, so that's what scale is. It's just the ratio between the real object and the thing that looks like it. Another example of where we use scale factor is in blueprints. Obviously, if you're going to build a house, you need to have some sort of visualization of it, and it'd be kind of ridiculous to have that on paper and have it be actual size of the house. All right, that'd be impossible to carry that paper around. So they make a much smaller version of the house and put it on paper. So they can see from here the dimensions of each room, and if you know the scale factor, you can predict how big that room is going to be in real life. So let's practice this idea by using some skills that we're going to need later on. So for instance, here we have two similar triangles. And this is definitely a big point in geometry, so you will definitely need this next year. What I'm going to do is I'm going to use this diagram here, and I'm going to use it to be able to predict this missing side here. So what I'm going to do is I'm going to set up a proportion and solve that proportion to figure out what x is. So first off, what's my scale? What's the ratio going from this one shape to the other shape? Well, it looks like this 6 kind of lines up with this 10. So I can start with the ratio 6/10. So 6 compared to that 10 will be equal to this 9 inches compared to x. So 9/x. So that's how I set up my proportion. Just go from one side in one shape to the corresponding side in the other shape, make one fraction, and then do the exact same thing for a different side. So let's go ahead and solve this. So 6 times x equals 9 times 10, which is 90. Divide by 6 on both sides, and I get x equals 15. Now another way we can do this is instead of comparing the 6 to the 10, I can compare this 6 to another side in the same figure. So I could start off comparing this 6 inches to this 9 inches. So if I start that pattern 6 inches compared to 9 inches, then over here on this similar figure, I need to do the same thing. This side, the 10 inches, compared to the x. So it's a different looking proportion, but when we solve it, I get 6 times x equals 9 times 10. Divide by 6 on both sides, I get the exact same answer. So the way you want to start your proportion is just pick a side and either compare it to the same side in the similar figure or compare it to a different side in the same shape. And then whatever pattern you start, keep that same pattern for the next fraction. Let's do another example. So here I've got 8 and 2 in the same figure, 16 and x in the other figure. So lots of ways I can start this. I can start by comparing 16 to x. So the long side over the short side. So then I come over to the other figure and I do the same thing, the long side over the short side. So 8 over 2. And that's a good proportion. All we got to do now is solve it. So 16 times 2 is 32. 8 times x is 8x. Divide by 8 on both sides. And I get x equals 4. Now, if you did it a little different way, but you still got x equals 4, that's fine. There's quite a few ways that you can set up this proportion, and it'll look different, but it'll still solve the same. All right, so let's try this same idea, but instead of geometric figures, let's go ahead and try to do it with some story problems that involve finding the heights of objects by using shadows. So it says a telephone booth that is 8 feet tall casts a shadow that is 4 foot long. Find the height of a lawn ornament that casts a 2-foot shadow. So what I'm going to do is, I'm a visual guy. I'm going to draw a picture here. So a telephone booth. For those of you who don't know, back in the day, we didn't all have cell phones. They had little booths in different places around the city, and inside this booth was a telephone. And you could get inside this booth, close the door, and put a quarter in, and then make a phone call. So that's what a telephone booth is. So I'm going to go ahead and draw the telephone booth. That's supposed to be a telephone. That's what they looked like back in the day. All right, and we know it's 8 feet tall. And it casts a shadow that is 4 feet long. So there's my shadow. Find the height of a lawn ornament that casts a 2-foot shadow. So okay, so there we've got a little lawn gnome. I have no idea how tall it is, but I do know that the shadow is 2 feet. And the height, what I'm looking for, that's my unknown. So I'll call that x. which begs the question, if I can measure the shadow, why can't I just measure the gnome? Nobody gnomes. So let's go ahead and set up a proportion. So if I take a look at this telephone booth, I can start with 8, or I can start with 4. It doesn't really matter. But I can start off with 8 compared to 4. Now, just to kind of keep things in order, what I did was I kind of labeled it, where I put the actual height on the top and then the shadow in the denominator. Okay, if you switch it up and did 4 over 8, that's fine. Okay, it doesn't really matter. As long as whatever pattern you set up in the first fraction, you follow that same pattern in the second fraction. So in the second fraction, I'm going to do the actual height over the shadow height. So my actual height, I have no idea. But the shadow height, I know to be 2 feet. So that's my proportion. 8 over 4 equals x over 2. So if I solve that, I get 16 equals 4x. Divide by 4, and I get x equals 4. So I know that the gnome, or the shadow, or the lawn ornament, is 4 feet tall. Now you might have looked at this and said, oh, this is pretty common sense. The shadow is half as much as the actual height. So if the shadow is 2 feet, that means that the lawn ornament has to be 4 feet. That's true. You noticed the pattern there and you went with it. That's some good intuition. However, if the numbers had been slightly different, like if this had been 9 compared to 4, it might have been a little bit trickier to do. So while this was an easy example and you could use common sense to figure it out, I would still encourage you know how to set up the proportion, because the numbers might not always be that easy. Let's do another one. A statue that is 12 feet tall casts a shadow that is 15 feet long. Find the length of the shadow that an 8-foot cardboard box casts. So again, I'm a visual guy. Let's go ahead and draw a picture. So here's my statue. And I know it's 12 feet tall. And the shadow is 15 feet. Find the length of the shadow that an 8-foot cardboard box casts. So let's draw a big old cardboard box. So we know that that is 8 feet tall. And we're looking for how tall or how long the shadow is. So now that we've got a visual diagram, we can go ahead and set up our proportion. Again, lots of different ways we can do this. I'm going to go ahead and compare the actual height of the statue compared to the actual height of the box. So since I'm comparing the statue to the box, I went ahead and labeled that. So the statue is on top, the box is on bottom. So then let's continue that same pattern with the shadows. So I have to put the shadow of the statue on top, and then the shadow of the box on bottom. So there we go. That's a good proportion. 12 over 8 equals 15 over x. Cross multiply. 8 times 15 is 120. Divide by 12. And I get x equals 10. So the length of the shadow caused by that box is a 10-foot shadow. All right, last example. Let's use a scale drawing in order to figure out some unknown quantities. So take a look at this sentence along with the diagram here. It says, the shoreline of the Great Bear Lake is approximately 2,719 kilometers, not counting the islands. If a map is drawn with a scale of 3 centimeters to 100 kilometers, how long would the shoreline be on the map? Okay, so we've read it. Let's take a look here. Some key things. right here, they give us a scale factor. So 3 centimeters to 100 kilometers. So anytime that they give you a scale factor, you can go ahead and use that as one of your fractions. So I'm going to go ahead and do that. 3 centimeters compared to 100 kilometers. So just to kind of make sure that I keep things labeled correctly, I'm going to make sure to represent that the 3 centimeters is on the map and the 100 kilometers is in real life. So if I go back and reread the problem, I see another piece of information in there, that the Great Bear Lake is approximately 2,719 kilometers. That's in real life. So I know that I'm going to go ahead and put 2,719, that's an ugly 7, kilometers. And it asks for how long would the shoreline be on the map. So that's my unknown. I'll put that right there. Now notice something else that I did. I went ahead and left the labels on there. 3 centimeters, 100 kilometers, okay, 2,719 kilometers. That's another way that you know that you're setting it up right. Here I had centimeters on top, kilometers on bottom. My unknown on top, kilometers on bottom. Because I have the same unit on bottom, that's a good heads up that I set up the proportion correctly. So let's go ahead and solve this. So if I do 3 times 2,719, get out my handy dandy calculator. 3 times 2,719. I get 8,157 equals 100x. Divide by 100 on both sides. And I get 81.57 equals x. So, because in the numerator I have 3 centimeters, I know that my unknown is going to be 81.75 centimeters. So if I could somehow measure the entire shoreline on this map, which I'm not going to draw the whole thing, all right? If I could measure that entire shoreline, I'm pretty sure that that would be 81.75 centimeters. So that's how we use proportions with a scale figure, is they will give you a scale factor. And you have to use that scale factor as one of your fractions, and then go ahead and set up the rest of the proportion. I hope this lesson wasn't too bad for you. If you guys have any questions, please feel free to email me or ask me in class. And hopefully you guys can get through the homework without any problem. You guys have a good one.